So in this video, we're going to go over a new concept known as the washer method. And the washer method is basically a build-up from the disk method. In the disk method, you were only given one radius. In the washer method, you're given two. So in this example, notice how the region's bounded by y equals x squared, y equals 3x about the x-axis. So the concepts are similar. It's just an extra step we have to take because notice how we're not abruptly given limits. We have to look for those, which we will get to. And we're given two radii instead of just one radius. So what does it look like? Well, we definitely have to know what it looks like. So let's start off with respect to x. So here we're given our x limit, and x to the left is xl, x to the right is xr. And we know this revolves about the x-axis. And we know these are the boundaries that are constraining that washer method, that area of integration. And I want you to notice right here, this line, we're going to call it ROX, which is the outer radius. The outer radius is known as ROX. RIX is known as the inner radius, and this is with respect to x. So the outer radius is this right here, where my mouse is, this right here, to the point of axis, to where the axis of revolution is occurring. The inner radius will be the function that is closer to the axis of revolution. So this line is closer to the axis of revolution, which is the x-axis. So now we're going to show this with respect to y. So we have our lower y limit, and we have our upper y limit. Yt is y top, yb is y bottom. And we have our constraints, and we have our area. So it's the same concept. So the inner radius is closer to the axis of revolution because in this case it's revolving about the y-axis. And the outer, the ROY, is the outer radius. So it's the revolution occurring about the y-axis. So this point right here where my mouse is the farther from the y-axis. So that's our outer radius. This point right here where my mouse is, this line, is closer to the y-axis. So that's our inner radius of axis of revolution. So again, this is about the x-axis and this is about the y-axis. And this is very important to familiarize yourself with the way these drawings look in order to do these type of problems. So now let's do the arithmetic. So the first thing we're going to do for a washer method is the same way we did this method. If you don't know how to do this method, watch that video first. I have a video on that in my Calc 2 playlist. Anyways, step one, we're going to sketch some graph. So this region is bounded by x equals y, or y equals x squared, y equals 3x, and it revolves about the x-axis. So we have our axes, and we know this line is y equals x squared, and this line is y equals 3x, right? And this revolves about the x-axis. So, and we have our limits. Because this revolves about the x-axis, our limits will be x limits. So we have our xl and xr, x to the left, x to the right. And that's what this drawing looks like. And the key right here is to identify the outer and inner radius. So note that the axis of revolution is about the x-axis. So which line is farther from it, the orange line or the teal line? Well, we can clearly see the distance between the orange line and the axis of revolution is greater, as the teal line is way closer to the x-axis, which is the axis of revolution. So our outer radius, our RO of x, will be the orange line, which is y equals 3x, and our RI of x, r subscript I of x, will be our inner radius, which is RI of x. So that's what our graph looks like. In drawing the graph is absolutely important. Before you solve the integral, you need to draw the graph so you know which line is closer to the x-axis and which line is farther from it. So now let's start to identify variables of integration. So for step 2, what we're going to do for the washer method is we're going to identify the variables of integration. So one thing I would like to do is I would like to familiarize this chart that I'm about to show you. So when to use r of x, and when to use r of y. So when to use r of x. We use r of x, and this is very similar to this method. Again, if you don't know this method, learn that first before you do Washer method, because you want to build your way up, not scale downwards. So r of x, when it revolves about the x-axis or any axis parallel with the x-axis, example given, when it revolves around the line y equals 1. Well, y equals 1 is parallel with the x-axis, so in that case, we would use r of x. Our limits must be x, r, and xl. And when to use r of y. R of y is when it revolves about the y-axis, basically the opposite of r of x, and any axis parallel with the y-axis. Example given, revolves about x equals 1, that's parallel with the y-axis, right? And our limits must be y limits, yt and yb, y top and y bottom. So again, this was what our sketch was. And note, very important note that we have here. So note, RO is farther from the axis of revolution, and RI is closer to the axis of revolution. RO is outside radius, RI is inner radius. So this was the drawing we had. This is what our sketch is supposed to look like. So now what we're going to do is we're going to identify the variables that we need for our integral. For our integral, we need the bounds of integration, and we need the RO and RI. R subscript O, R subscript I, functions of x. So the first thing we're going to do is identify our R of I, our inner radius. We can easily see that it's x squared because x squared is closer to the axis of revolution. Thus our R of O is equal to 3x, the line farther from the axis of revolution. But for Washer method, as for this method, we need to square these. So Ri squared is equal to x squared to the square, which is equal to x to the 4th power when we distribute the exponent. And Ro squared, the outer radius squared, is equal to 3x squared. And we square the 3 and the x, which is 9x squared. So that's our outer radius. So now we need the variables. Now that we have the functions, our inner and outer radius, we need the limits of integration, which is different from Washer method, from this method. So now for step 3, what we're going to do is we're going to find the limits of integration, because that's what we need in order to set up our Washer method integration. So the first thing we do need to know is that we're not explicitly given the limits of integration as we are in this method. So since we're not given the limits of integration, we're going to have to find them. How do we find them? Well, we're given two functions, the outer radius and the inner radius. So what we're going to do is we're going to set those equal to each other. Set R subscript O equal to R subscript I. So our R of O is equal to 3x, the outer radius. Our R of I, the inner radius, was equal to x squared. Notice it's RO and RI, not the squared, because when we squared them, that's what we're plugging into our integral. But when we're finding our limits of integration, it's RO and RI without being squared. So I do want you to keep that in mind because that's a common mistake where people fall. So do not assume this is RO squared and RI squared. It's RO is equal to RI. And what we're going to do is we're going to solve for x given the sketch. So we know from the sketch that the lines intersect at two different points. Those two different intersection points are the limits of integration. And we know the original, they start at the origin. So we know our lower limit is equal to 0. However, our upper limit, we do have to solve for it by setting these two equal to each other. And I do want to familiarize the naming convention that I use for limit variables. I think helps out a lot of people. Yt is top limit y, yb is bottom limit y, xr is right limit x, xl is left limit x. So you can use whatever naming convention you want. I think this works better than using A, B, C, D, or whatever. It's up to you. But this is the naming convention I use. So when you see this, know that these are my limit variables the way I like to identify them. So now 3x is equal to x squared. So we're trying to solve for x, essentially, in essence. So 3x is equal to x times x, because the x squared is x times x. So we can cancel out an x on each side. and we're left with x is equal to 3. Thus, we know our left limit is x equals 0 as we saw from the sketch, and our right limit is x is equal to 3. So those are our limits. And also now we need to know what we're going to set up our integral now that we have our limit variables and we have our two functions, r(o) squared and r(i) squared. So we're going to bring them back, recall them real quick. R(i) squared came out to be x to the 4th power, and the outer radius squared came out to be 9x squared. Note, please note that, I will say it again because it happens a lot, we're setting the radii equal to each other, r(o) and r(i), not the radii squared, the radii. Notice we did not set x to the 4th equal to 9x squared. If you do that, you're going to get a different answer. So now what we're going to do is we're going to set up the integral. So the formula is, since this is with respect to x, it's very similar to this method formula. So xl goes to xr, r of ox squared, the outer radius squared minus the inner radius squared, with terms of x, so dx. And we have all the variables right here, so we're going to plug them in. So the volume is equal to pi. The left x is 0, the right x is 3. The outer radius is 9x squared, and the inner radius is x to the 4th power times dx. So for step 5, we're going to integrate this function. So the integral is very easy. I think the trivial part is setting up the integral. Setting up the integral is where people fall. But once you know how to integrate this, the integral itself is very easy to compute. So the volume of pi is equal to 9x squared cubed, 9x squared. When we integrate that, it's 9x cubed over 3 minus x to the 4th is x to the 5th over 5. Bounded between 3 and 0. So now let's plug in the bounds. So now we're going to plug in the bounds. So that's what we're going to do for step 6 and solve this integral. So we know the volume is equal to pi 3x cubed, because 9 over 3 is 3, so it simplifies to 3x cubed, minus x to the 5th over 5, bounded from 0 to 3. So what we're going to do is we're going to go ahead and plug in the bounds. So 3x cubed minus 3 to the 5th power over 5 minus 3 0 cubed minus 0 to the 5th power over 5. And it's very important to use parentheses, so please use them because it prevents a lot of error. So what we know is that these terms will zero each other out, and what we're left with is the volume is equal to pi times 3 to the 1 power times 3 to the 3rd power is 3 to the 4th power, which is 81, minus 3 to the 5th power, which is 243 over 5. Minus, of course, in the yellow parentheses is 0. So that term again zeroes out. So what are we left with? The volume is equal to pi, parentheses, 81 minus 243 over 5. And what we're going to do is we want to have a common denominator, so that way it makes it easier to compute this. So we're going to do this by multiplying the first term, 81, by 5 over 5. We're multiplying it by 1, but now it has the same denominator as the second term, 243 over 5. In doing so, we get pi is equal to 405 over 5 minus 243 over 5. And when we simplify this, we get 162 over 5. So all I did was subtract 405 minus 243. So our volume is 162 over 5 pi. So that's the answer to this problem. So yeah, washer method is a step above this method. It's a little bit more trivial because we do have to find the bounds of integration instead of just being given to us. But let's do more examples so we can familiarize ourselves even better with this washer method concept. So in this example, we're given the region bounded by x equals the square root of y, x equals 2y, and it's about the y-axis. So first thing we're going to do, as we did in the previous problem, is we're going to sketch a graph. So our x and y-axis, we know this revolves about the y-axis. So we know this needs to be in terms of y, but we'll get to that later. So for now, we're going to just sketch this out. So we know this line is the square root of y, and we know this line is x equals 2y. And the area involved is this shaded region right here. So which one's the outer, which one's the r naught y, or r0, or r o y, and which one's the r I y? So the line that's farther from the y-axis is considered the axis of revolution, is considered to be the outer radius. So in this case, notice the teal line is farther from the y-axis. It's farther from the y-axis of revolution. So the teal line will be our outer radius, thus making the orange line our inner radius. So one thing I do want you to notice is in the previous problem, this revolved about the x-axis, and you might have been tempted to say that the teal line is closer to the x-axis. While that is true, we're revolving about the y-axis. Since it's revolving about the y-axis, we must make a note that we're distancing whichever one is farther from the y-axis. So we can clearly see the orange line is closer to the y-axis and the teal one is farther. So do keep that in mind. So now let's set up the variables of integration. So for step 2, we're going to identify the variables of integration. And again, I'll familiarize yourself with this chart. Make note of it if you haven't yet. I think it makes it easier to solve. And I want to make a note that the RO is farther from the axis of revolution and the RI is closer to the axis of revolution. So in this case, this was what our graph looked like. Our sketch looked like this. And we identified our outer radius and our inner radius. So what we do need to do now is we need to identify which one's which. And so we're going to do this. So the inner radius, as we can see, is that orange line, which is x equals 2y. Our outer radius is x equals the root of y, the square root of y. And now for our integral, we do need to square both of these. So the inner radius squared is equal to 2y squared, and 2y squared is equal to 4y squared. 2y parentheses squared is equal to 4y squared. And our outer radius with respect to y squared is the square root of y squared, and the square root and the radical cancel out, so our outer radius squared is equal to y. So now let's find our limits of integration. So now for step 3, we're going to find the limits of integration. So in doing so, we know that we have to set up the outer and inner radius equal to each other and solve for the y variable. So our outer radius, and again I'll say it, it's the outer and inner radius, not the outer radius squared and the inner radius squared. If you do that, you're going to get a different answer, so do not do that. So the outer radius is, the inner radius was equal to 2y, and the outer radius was equal to the square root of y. So we're going to set these equal to each other. So 2y is equal to the square root of y, and we're going to solve for this by isolating the y. So what we're going to do is we're going to square both sides, and we get 4y squared is equal to y. Thus 4y squared is equal to 4 times y, and is equal to y. And we're going to divide both sides by y, just so we can get y by itself. And what we're left with is 4y is equal to 1. And when we solve for y, we get y is equal to 4, 1 over 4. And we know that the lower limit, our limit variables, we know our top limit y is equal to 1/4. Our bottom limit y is equal to 0, because when we drew the sketch, it started at the origin. So that's how we know our bottom limit y is 0, our top limit y is equal to 1/4, the one we computed. So now let's set up the integral. So to set up the integral, we do need ry squared, which is equal to 4y squared, and we do need the outer radius squared, which was equal to y. So now let's set it up. So the formula is right here. Pi is equal to pi of the integral of the lower bound y to the upper bound y of the outer radius squared minus the inner radius squared times dy, because this is all with respect to y. And when we plug in the points, we get pi from 0 to 1/4 of the outer radius, which is y minus 4y squared, times dy. And in step 5, we're going to integrate this. So the integral is very easy. Again, washer method. The hard part is setting it up. The easy part is computing, because the integral is usually not too trivial most of the time. So when we integrate this, we get the volume of pi of y. The first term would be y squared over 2. The second term, 4y squared, would be y cubed over 3 times 4, bounded between 0 to 1/4. So now let's plug in the bounds. So now for step 6, we're going to plug in the bounds and solve. So our volume, when we plug in the bounds from 1/4 to 0, we get this right here. So this is our original integral from 0 to 1/4 of y squared over 2 minus 4y cubed over 3. One thing I do want you to note is it makes it a lot easier when you have a common denominator, so you can factor it out. So that's what we're going to do. So we're going to have a common denominator of what's the least common multiple of 2 and 3? It's 6. So we're going to have a common denominator of 6. So we multiply each term by a fraction that's equal to 1. So the first term we'd multiply by 3 over 3. The second term we'd multiply by 2 over 2. So we have a common fraction. And we're not changing the value since it's technically still multiplying by 1. So in doing so, we get the volume of 3y squared over 6 minus 8y cubed over 6. And in doing so, this is again being bounded from 0 to 1/4. We get the volume of pi over 6 of 3y squared minus 8y cubed from 0 to 1/4. So now we can just plug in what we have. So that's exactly what we're going to do. We know pi over 6 is bounded from 3 to 1/4 squared minus 8, 1/4 cubed, minus 3. We plug in 0 now. And in doing so, we know these terms both go to 0 because we're plugging in 0. And when we compute this, we get pi over 6, 3 over 16, because 1/4 squared is 1 over 16, times 3 is 3 over 16, minus 8 over 64, minus, of course, 0. And that term obviously goes to 0. So again, we do need a common denominator to solve this. So pi over 6, 3 over 16 minus 2 over 16, because 8 over 64 is the same as 2 over 16. And now we can simplify this. So pi over 6 divided by 1 over 16 times 1 over 16 is equal to pi over 96. And that's the answer. So it makes it easier whenever you try to have a common denominator and factor out when you're plugging in terms. It prevents error. So let's move on to the next problem. So in this example, we're given a term, region bounded by the first quadrant, y equals x cubed, x equals y over 2, and it's about the x-axis. So one thing I do want you to notice right off the bat is where my mouse is. We're given y equals x cubed and x equals y over 2. So we're given something in terms of y and something in terms of x. So how do we know which one to use? Well, since it's revolving about the x-axis, we know this needs to be in terms of x. So now, without further ado, let's move on to step 1. We're going to sketch a graph. So we have our x-axis and we have our y-axis, and it's revolved about the x-axis. So this line right here is x equals y over 2, and the teal line is x equals y cubed, or y equals x cubed. And notice how the teal line would also go right here in this negative quadrant, the third quadrant, but since this is restrained to be first quadrant, the graph will look like this. So now what we're going to do is we're going to identify the outer and inner radius. The outer radius, of course, is farther from the x-axis, would be the orange line, x equals y over 2. The inner radius with respect to x would be the teal line because it's closer to the x-axis, which is y equals x cubed. Again, I'm choosing x because it's revolves about the x-axis. So let's move on to the next step. So now for step 2, we're going to identify the variables of integration. Again, we're going to use this chart as a reference because it's a very helpful chart. And basically, when it revolves about the x-axis and when it revolves about the y-axis. So we already know this revolves about the x-axis because since it revolves about the x-axis, we're going to use r of x. And the sketch looks something like this, as we already drew it out. And we already identified our outer and inner radius. And note that the RO subscript O is the outer radius, R subscript I is the inner radius. So since it revolves about the x-axis, all functions must be in x terms. So y equals x cubed. However, our other function is x equals y over 2. this has to be in terms of x. So let's go solve for y. So when we solve for y, we get y is equal to 2x. So now our inner radius is the teal line, which is y equals x cubed. Our outer radius, which is the orange line, is equal to y equals 2x. Now that we solved it in terms of x. And when we square these, because we need to, because this is a washer method problem, the inner radius squared would be x cubed squared, which is equal to x to the 6th power. When we apply the properties of the exponents, it's x cubed is 3 times 2 is 6. And the outer radius, when we square it, is 2x squared. 2x parentheses squared, so we square each term, so it would be 4x squared. So now let's find the limits. So now for step 3, we're going to find the limits of integration. Same process. We're given our r of ix and our r of ox, our outer and inner radii, x cubed and 2x. And we're going to set these equal to each other, and we're going to solve for x as we've been doing in the previous problems. So 2x is equal to x cubed. So 2x is equal to x times x times x. That's our x cubed. And right off the bat, we can cancel out an x. So we're left with 2 is equal to x squared. But we're trying to solve this for x. So we're going to take the square root of both sides. And we're left with x is equal to the square root of 2. Plus or minus the square root of 2. However, keep in mind that this region is bounded to the first quadrant only. It's only bounded to the first quadrant, which means that we omit the x is equal to negative 2, negative square root of 2, and we only focus on x is equal to the root of 2, the positive root of 2. So thus we have our limit variables, as you should be familiar with by now. And we identify our left x limit as x equals 0, our right x limit as x is equal to the positive square root of 2. So we're going to draw a line. And now, step 4, we're going to set up our integral. So we know the formula is the volume is equal to the bounds of the left limit x to the right limit of x of the outer radius squared minus the inner radius squared times dx. And we have the variables of the left limit x and the right limit x. So now we're going to plug in the inner and outer radii squared, which was x to the 6 and 4x squared. So now we're going to plug these in. So we're going to plug in all the variables that we have. So pi from 0 to positive square root of 2 of the outer radii, which is 4x squared minus x to the 6 times dx. And for step 5, we're going to go ahead and integrate this function. When we do that, we get the volume is from pi of 4x squared is 4x cubed over 3 minus x to the 6 is x to the 7th over 7. And this is bounded from 0 to the positive root of 2. So now let's plug this in. So now we're going to plug in the bounds and solve this. So our volume is equal to 4 over 3 x cubed minus x to the 7th over 7, bounded from 0 to the square root of 2, positive square root of 2. And all we're simply going to do is just plug in the bounds. So 4 over 3 times this positive root of 2 cubed minus the positive root of 2 over 7 to the 7th power. And note the 7th power only applies to what's in parentheses, so it does not apply to the 7 on the denominator. Keep that in mind. Minus 4 over 3 times 0 to the 3rd power minus this 0 to the 7th power over 7. We know those terms zero out, and what we're left with is the volume of pi over 3 times 4 over 3, 2 to the raised to the 3 over 2, divided by 2 raised to the 7th over 2. And how did I do that? I did that because the square root is also equal to the 1/2 power. So 1/2 times 3 is 3 over 2, 1/2 times 7 is 7 over 2. So, and of course minus 0. So when I plug this into my calculator, I got 2.256. Thanks for watching. I hope this example was helpful. So in this example, again, the region is bounded by the first quadrant, x equals y squared, y equals 2x, and it's about the y-axis. Right off the bat, by now we should know it's revolving about the y-axis, so we're going to use terms of r of y. So we're going to sketch the graph, and we know this revolves about the y-axis, and we're going to draw the lines. So this line right here, the teal line is x equals y squared, and the orange line is y equals 2x. And we know the inner radius is closer to the y-axis of, which is the teal line, and the outer radius is the line farther from the y-axis, which is the orange line. Now let's solve for the variables of integration. Step 2, we're going to identify the variables of integration. So again, we're going to reference this chart that I have right here. Make note of it if you haven't yet. And we're going to make a note that the outer radius is RO, farther from the axis of revolution. The inner radius RI is closer to the axis of revolution. So we know our axis of revolution is the y-axis. So we know our outer radii is the orange line and our inner radii is the teal line. We know y equals 2x is the outer radii and x equals y squared is the inner radii. But note, are we going to use r of x or r of y? Well, since it's revolved about the y-axis, we're going to use y terms. So we're going to use r of y. So now that we have the sketch, we're going to identify the inner and outer radii. So we know the inner radii is the teal line, which is x equals y squared, and the outer radii is y equals x squared, or y equals 2x. So what we have to do is, since it revolves about the y, we want this in y terms. So we have y equals 2x, but we want this in terms of y. So all we're simply going to do is just literally just solve for x. And when we do that, we get x is equal to y over 2. So now we can start to identify what we have. So the outer radii of y is equal to y over 2 in terms of y. The inner radii of y is equal to y squared. And now when we square these, because we need to square them for the integral, we get y over 2 squared, which is y squared over 4. And the inner radii squared, when we square it, is y squared, which is y to the 4th power. So now for step 3, we're going to find the limits of integration. As we've done, we're going to set the outer and inner radii equal to each other. Recall the outer radii was y over 2. The inner radii was y squared. So y over 2 is equal to y squared. And note again, this is not the squared terms. This is just the inner and outer radii. If you use the outer radii squared and the inner radii squared, you're going to get a different answer. So when we compute this, we can solve. We're trying to solve for y, as I'm doing right here. Cancel the y's out. And these are the limit variable conventions that I use. So the bottom limit of y is equal to 0. The upper limit of y that we just solved for, when those two y's cancel, we're left with y equals 1/2. So the upper limit is going to be 1 over 2. So now let's set up the integral. So we know the volume is pi. With respect to y, it's the bottom y limit to the upper y limit of the outer radii y squared minus the inner radii squared with respect to dy. So the outer radii and the inner radii squared were equal to y squared over 4 and y to the 4th power. So now we're going to plug these in. So pi from 0 to 1/2, bounded from y squared over 2 to minus y to the 4th power times dy. So now we're going to integrate this function. So the volume, when we integrate y squared over 2, y squared over 4, we get 1/4 the constant times the integral of the y term, which is y cubed over 3. And then y to the 4th power integrated is y to the 5th over 5. And this is bounded from 1/2 to 0. So now let's plug in the bounds. So now we're going to plug in the bounds and solve this. So our integral was y cubed over 12 minus y to the fifth, because 1/4 times y third over 3 is 1 over 12, bounded from 0 to 1/2. So now what we're going to do is, just to make this a little easier when we plug this in, we're going to have a common denominator. So we want a common denominator, least common multiple of 5 and 12, 60. So we'll multiply that term by 5 over 5, multiply the second term by 12 over 12, bounded from 0 to 1/2. It makes it easier when we plug it in. So now we have 5y cubed over 60 minus 12y to the fifth over 60, bounded from 0 to 1/2. So thus we can pull out the 1 over 60, and we're left with pi over 60. And now we have one line, 5y cubed minus 12y to the fifth power, bounded from 0 to 1/2. So now we're going to plug everything in. So the volume from pi over 60 of 5y to the 1/2 cubed minus 12 to the 1/2 to the fifth power minus 5 to the 0 cubed minus 12 to 0 to the fifth power. And we know those terms will go to 0. And what we're left with is pi over 60 times 5 over 8, because 1/2 cubed is 1 over 8, minus 12 to the 1/2 to the 1/2 to the fifth power, which is 1 over 32, minus, of course, 0. And what we're left with is pi over 60, and we want a common denominator, so 5 over 8 minus 12 over 32, and we want a common denominator, so we're going to multiply the first term by 4 over 4, so we can have that common denominator, and we're left with pi over 60 times 20 over 32 minus 12 over 32, which in essence is equal to pi over 60 times 12 over 38 over 32, which is equivalent to 1 over 4, which is equivalent to 1 over 4 times pi over 60 is pi times divided by 60 times 4, which is equal to pi over 240. And that's the answer. Thank you for watching. I hope this was helpful.